Hey everybody. So as we come back, we are now going to be starting to look at truth tables. Well, what is a truth table? A truth table is a definition. It doesn't look much like a definition, but that's the right way to think about these things. What we are doing with our truth tables, first and foremost, is we are providing truth and falsity based definitions of the logical operators. For example, look in the bottom right corner. Look, that's where I'm at. Let me try again. So if you look in the bottom right corner now, then you will see that we've got a table that has, well, you've got the column headers at the top, and then you have two rows. If we look at the left-hand side of this bottom right one, the not one, we see that underneath P, there are two lines listed, T for true and F for false. What we're doing here with the truth table is that we are laying out every possible way that the world could be relative to the statements that we are considering. So in the not table on the bottom right, well, we're only looking at one statement, P, and there are only two possibilities within this system of logic. Either P is true or P is false. I think this actually would be a good time to pause and think about a little bit about how this connects up with real life and real logic. In a sense, what we are working with here is a game. It is a game that has very precise rules that ensures that the game, if played correctly, will be an extremely logical game. A game where no logical missteps are even possible, so long as you follow the rules. But there are downsides to this. There are shortcomings and limitations to a system of logic that gives an absolute guarantee of truth, an absolute guarantee of logically correct form. And that's that we have to make quite a few simplifying assumptions in order to get that result. And well, one of the really critical simplifying assumptions that we make in this system of logic is that every single statement is either true or false and not both. Arguably, that does not hold in the real world. I think about kind of boring cases where we've got, I don't know, like a glass that's half full, or is it half empty, right? And so the statement, this glass is empty, or this glass is full, neither of them are going to be 100% true of a glass that is half full. Like it's sort of full and it's sort of empty. Well, this system of logic is not going to permit that kind of subtlety. If you need that kind of subtlety, that subtlety will have to be built into the content within the statement. So we could have a statement, we'll call it P, where P could represent the claim that the glass is half full. And we could say that that's true. But if we have some other letter, say G, and G stands for the claim that the glass is full, well, within this system of logic, we've got to make a choice. We have to either decide that that statement is true or that it's false. We can't have like a fuzzy middle ground where it's sort of true and sort of false. So anyways, that's just something to keep in mind, is that we are assuming, kind of for the sake of getting the benefits of such a rigid and robust logical game, we are going to assume for the sake of that every single statement must be one or the other, must be true or must be false, right? Whether we know it or not. All right, so with that qualification in mind, when we look at the truth table for not, we see that there are just two possibilities for P. Right? That's the rule of the game here, is that every statement is either true, 100% true without qualification, or that it's false, 100% without qualification. So given that there are these two possibilities for P, then we have laid out every possibility, every possible way that the world could be with respect to that one statement. Now then you'll notice on the right, on the other side of a line, we have a tilde P, which means not P, the claim that P is false. When will it be true that P is false? Well, namely when P is false, right? So if you look at the truth table, you'll see that where P is true, the not P is false, and where P is false, not P is true. The tilde, the definition of a tilde within this system, the definition of the negation is that it reverses the truth value of whatever it applies to. So if it applies to a single statement, then that statement's truth value is flipped. If the statement is true, it becomes the not that statement is false, and vice versa. And then we keep in mind, we can also put a tilde around larger collections of statements, as we've seen in the previous videos, that we could say it is not the case that, and then in parentheses, X and Y. And what we're saying by the tilde around X and Y is it's not the case that they're both true. They could both be false. One of them could be false and one of them is true, or vice versa. But the negating the and, this and that in parentheses, is a negation of that entire thing. And so you would flip the truth value for the entirety of that and statement. Well, let's talk about that. We've got a truth table for and you'll notice that there are 4 rows below the line rather than just 2. And that's because we're working with 2 different statements, P and Q. They really should use letters that look less similar to each other, whatever. So when you've got 2 statements, you actually have 4 possibilities. Like P is true or P is false, Q is true or Q is false. And you have to consider all the different combinations thereof. So, it's possible that they're both true, that they're both false, or that one is true and one is false, or vice versa. If we had 3 letters, then we would have to have 8 lines below that top line. There would have to be 8 different rows in our truth table, because, well, it just keeps doubling, because every time you add a new variable in a binary system meaning that every statement is either true or false, well, then there are 2 more possibilities to consider, multiplied by all the other possibilities that we had already considered. So just as we double from 2 to 4 when moving from 1 to 2 statements, we double from 4 to 8 when we move from 2 statements to 3. Okay, but we're not working with 3 right now. We just got 2, which is great because long truth tables are kind of a pain in the butt and annoying. Looking at the truth table for the and, what we see is that P and Q will only be correct, it'll only be true that both of them are true. Well, unsurprisingly, in the one scenario where both of them are true, right? If P and Q are both true, then the conjunction is correct. But if either one of them is not, then it is false. Okay, now, coming back to what I was talking about with the tilde earlier, I'm going to add another row to the truth table for and, just to show how this would work, where I put a tilde around both P and Q. So I'm not saying that P is false. I'm not saying that Q is false. I'll go ahead and use the dot since that's what I got already up here. All right, well, that's a little sloppy. Oh well. When I negate P and Q, what I do is I reverse the truth values of each line of the truth table. Right? And so line 1, it is true that P and Q. Therefore, the negation of P and Q is going to be false. When P is true and Q is true, in that first row, while it's true that they're both true, it is false that both of them are false. Obviously, right? And then we would also reverse the truth values for the other 3 lines, right? And so that's what a tilde does. A tilde is just reversing it from, well, I like to think about this in more kind of computer terms, turns a 1 into a 0. So it turns T into F, and then I think of F, like the false, as being a 0. The negation is turning a 0 into a 1. And that's just one way of thinking about it. All right, so negation is flipping the truth value of whatever it is that it applies to. Keep in mind that if it applies to parentheses, you have to reverse the truth value of the entire statement in parentheses. We're not just saying that P is false when there's the parentheses there. Okay, so that's the and. Very restrictive. An and claim is only true when both of the conjuncts are correct. With the or, we see a much more permissive truth table, where saying either P is true or Q is true, That will be true just so long as either one of them is true. This is what's called the inclusive OR, as opposed to an exclusive OR. The inclusive OR is the one we're working with. This is the one that says that this thing is true, that thing is true, or they are both true. And it's that last part, the or they are both true, that makes it an inclusive OR. The exclusive OR, which we're not going to work with, I don't mean to confuse you here, but the exclusive OR is maybe a little closer to what we sometimes mean in ordinary English when we use an OR claim. Oftentimes when I give somebody an OR, like I don't know, talking to my kids, and I say, okay, well, either we can go get ice cream or we can go to the park. If my 5-year-old responded by saying, yes, Daddy, I really, really like that inclusive disjunction. Who talks that way? Anyway, so if my 5-year-old said, oh yeah, I really love that inclusive disjunction, let's do both of them. Then I would have to clarify, say, oh no, sorry, these are not, it's not an option to do both of them. You have to pick one or the other. I would be using the exclusive OR, and the exclusive OR would have an F in row 1, saying they can't both be true, but that's not what we're working with, right? So I don't know, just trying to highlight the difference. So what we're working with is the inclusive OR that is true in 3 out of the 4 cases. The only time that the inclusive OR is going to be false is when both of the disjuncts are false, both the thing to the left of the OR and the thing to the right of the OR. When both of those are incorrect, we say it's incorrect to claim that one or the other must be true. Okay, so far so good. I feel like these first 3 are fairly intuitive. It's a little weirder when we get to the conditional, what the book represents as a horseshoe. The way I think about the truth tables for the conditionals is that a conditional claim is assumed to be true unless it is proven false. That's the way that I think about the conditional here. So what we're saying in the conditional is that if P is true, then Q must be true. Well, how do we know whether that's correct? Well, it's actually very tricky to figure out how you would prove a conditional true. I mean, you can show that P is true, and you could show that Q is true. But simply showing that both of them are true is not enough to show that one of them proves the other, or that the truth of one is dependent on the other. But it's hard. It's hard to imagine, or it's very tricky to show how we could absolutely prove positively that one thing leads to another, or that it entails the other. But I do have a pretty good sense of how we could prove a conditional false, and that's if the condition was met, and yet the consequent did not follow. So it's like, if I don't know, if somebody says to me, give me all your money, or I will punch you in the face, and I say, oh, I'm not giving you my money. And then they don't punch me in the face. They're like, oh, well, I just proved that your conditional was false, Mr. or Mrs. Mugger, robber person. You claimed that one thing would logically guarantee the other, and yet here we are where I didn't give you my money and you're not punching me in the face. So the conditional is definitely false in line 2. If the antecedent is correct, but the consequent is false, if the condition that the conditional claims will lead to the consequent happens, but then we don't see the consequent, that shows that the conditional is incorrect. Right? And so line 2 is the one and only time where we will mark a conditional as false. Now, there actually are some other reasons for setting it up this way that have to do with the biconditional, which I'll get to in just a little bit. But well, let me just go ahead and do this now. If we were to have a biconditional, I'll go ahead and write it next to our original one here. I'm going to go ahead and use my arrow symbol. The book uses 3 lines. I mean, that's fine. You can use the book symbols. I like the arrows, though. When I write the arrows clearly, they help me to see the logic a little bit better. All right, so biconditional is saying that P is true if and only if Q is true. Another way of thinking about this is that it is combining 2 different conditionals together. It is saying if P then Q and if Q then P. And so it's only going to be true when both sides of that are true. When P and Q are both true, or when P and Q are both false. But the biconditional will be incorrect anytime that the two different statements don't have the same truth value. All right, so we'll leave it at that.